Okay, in this lesson we're going to be looking at Unit 6, Chapter 6, Trigonometric Identities. We're still solving trigonometric equations using identities. This is Part 3. And we're going to be solving trigonometric equations and we're looking at general solutions. Okay, as we said, this is from Section 6.4, solving trigonometric equations using identities. And the focus is going to be on finding the general solutions to trigonometric equations using identities. Okay, example 1. Determine the general solution for a trigonometric equation. Let's solve the equation sin 2x equals root 2 cosine x algebraically and give the solution expressed in radians. Okay, sin 2x equals root 2 cosine x. You should recognize that we're going to need to replace sin 2x here, and when we replace sin 2x using one of our identities, we're going to get 2 sin x cosine x, that is the same as sin 2x, equals root 2 cosine x. If I bring the root 2 cosine x over to the left side, which is normally what we do to get the equation, to solve an equation, we normally get it equal to 0. And now if you look at this equation, you should see that although I have two trig functions here, both sine and cosine, if I remove a common factor of cosine x, I will simplify this pretty nicely here. And I get cosine x inside of 2 sin x subtract root 2. Now using the zero product property, I got cosine x equals 0. And I got 2 sin x subtract root 2 equals 0. Solving this one here for sin x, we get 2 sin x equals root 2. So of course sin x equals root 2 over 2. So again, we have two equations here. We got cosine x equals 0, and we got sin x equals root 2 over 2. Now remember, we're looking for the general solution. Determine the general solution expressed in radians. So where is cosine x equal to 0? Well, again, let's use our unit circle to help us determine that. Give me a second here to draw it for you. So we use the unit circle and we plot our points on the unit circle. Here's the point x is 1, y is 0, 0, 1, negative 1, 0, and 0, negative 1. So we're looking at where is cosine x equal to 0. Cosine is the first coordinate. So you can see that cosine x is equal to 0 here and here, which would be at 90 and 270. Now you've got to think about how can we represent all the possible solutions though, not just 90 and 270, because there are many more locations. As we continue to rotate around this unit circle, whether we go in the positive direction or the negative direction, there will be many solutions other than just 90 and 270. Certainly in one rotation it's the only two answers, but we know that it continues on. We need to represent all the possible solutions for x where cosine x equals 0. And the answer is simply going to be, at pi over 2, there's one solution at pi over 2. The next solution occurs pi radians beyond that. The next solution will occur pi radians beyond that, and so on. So I can simply write my answer as x equals pi over 2 plus pi over 2, and where n is the number of I. Let me just move this over a little bit here so that it doesn't look quite as squat in there. Let me just fix that. Where n is the number of I. Here we go. So that will represent all possible solutions for cosine x equals 0. Now, where is cosine x equal to root 2 over 2? Well, you should recognize that as a special case. Where is sine positive? I may have said cosine, but where is sine x equal to root 2 over 2? Where is sine positive root 2 over 2? Well, using the cast rule, C-A-S-T, sine is positive in these two quadrants here. So this solution here will occur at, you should recognize root 2 over 2 as a reference angle of 45 degrees, or in radians, pi over 4. So one answer here will be pi over 4 plus 2 pi n, where n is the number of I. And the other answer is right here, which is 3 pi over 4 plus 2 pi n. where n is the number of I. So these are our three solutions. Here, here, and here. These two solutions cannot be combined into a single solution. If the two terminal arms form a straight line, then they can be combined into a single solution. Here they do not. That's why we combine these two solutions here. The pi over 2 and the 3 pi over 2, we combine them into a single solution because they form a straight line, both terminal arms. And we can do that in that case. But here we cannot. So these are our three solutions. Now we should always check for non-permissible values. But if you look at the equation sine x and cosine x, there are no non-permissible values here because there's no restrictions on sine and cosine. So we don't have to worry about that. But it's always a good idea to check. Example 2. This time we're going to be using reciprocal identities to help us determine the general solution to a trig equation. It says algebraically solve 2 sine x equals 7 subtract 3 cosecant x. Let's do that. I got 2 sine x equals 7 subtract 3 times cosecant is 1 over sine. Now the question is, what do we do in this case? How do we make this equation look a little nicer than what it is there now? Well, one thing we can do is we can get rid of the denominator of sine x if we multiplied everything, both sides of the equation, by sine x. Let's do that. That gets rid of that denominator of sine x that you see there. So I got 2 sine squared x equals 7 sine x subtract 3 times 1, which is 3. Now if I rewrite this by bringing everything over to the left side of the equation, you should recognize that as a quadratic, that is factorable. So that's factored. Hopefully it's factorable. Now, the method that I use for factoring is trial and error method. I'm sure some of you use decomposition. Someone may use the box method that you may have learned in level 1. But regardless of the method you use, you need to know how to factor this. So I got 2 sine x, I want 3 and 1. So I'm going to try 1 and 3 here. That's why it's called trial and error. Okay, let's see if this is going to give me my middle term. I want a negative 7x, negative 7 sine x. I got a 1 sine x and a 6 sine x will give me a 7 sine x. So that tells me I probably got this written out correctly here. So I need a negative 7, so both of these would have to be negative. Now I always double check my factoring. 2 sine x times sine x is 2 sine squared. I got 2 sine x times a negative 3. That's a negative 6 sine x. Negative 1 times sine x is a negative 1 sine x. So a negative 6 and a negative 1 is a negative 7, so that's good. And a negative 1 times a negative 3 is a positive 3. Always check your factoring. There's no reason to get factoring incorrect. So I got to factor correctly. Now I use the zero product property. 2 sine x subtract 1 equals 0. And sine x subtract 3 equals 0. So of course I get 2 sine x equals 1. So sine x equals 1 over 2. And sine x equals 3. So again, we have two equations to solve. I got sine x equals a half and sine x equals 3. You should immediately recognize, though, that sine x equals 3 is undefined. It's undefined because sine x cannot equal a value greater than 1 or less than negative 1. And if you think about the graph of sine x, that makes perfectly good sense, right? Here's the graph of sine x. Sine x oscillates between 1 and negative 1. The value of sine x will never exceed 1 or be less than negative 1. So a value of sine x equal to 3 is undefined. So we really only have to concern ourselves with one equation, and that's sine x equals a half. So where is sine x equal to a half? Well, let's see. Sine x equal to a half, we're going to use our unit circle to help us determine that. Sine x is equal to a half. We've got to consider the fact that sine is positive in 2 quadrants. Don't forget that. Sine is positive here and here, so here's where our 2 terminal arms will be located. Sine is the second coordinate of this point. So the coordinates of that point would have sine of a half. You think about the point, the cosine got to be root 3 over 2. My reference angle in this case is 30 degrees or pi over 6. So my general solution, there are 2 general solutions. X equals pi over 6 plus 2 pi n, where n is the number of I. That's the first general solution. The second general solution will be 5 pi over 6 plus 2 pi n, where n is the number of I. Now remember, we should always check for non-permissible values. If I look up at the original equation, I can see that cosecant does have non-permissible values, because cosecant is equal to 1 over sine. So this is going to be undefined when sine x is equal to 0, because we cannot have sine x equal to 0. Sine x equal to 0 at any of these answers that I have here. And the answer is no. Sine x is equal to 0 here and here. Here's where your non-permissible values will occur. At 0 and at 180, or at 0 and pi and 2 pi and so on. Not at any of these solutions, but I did check. These are all valid solutions because sine x cannot equal 0, and sine x will only equal 0 at values of 0, pi, 2 pi, negative pi, and so on. Okay? So we're good. Here's my solution. Right here. Here's a multiple choice question that involves finding the general solution in radians. It might be a good idea for you to try this question first before you actually watch me do it. Okay, we have sine 2x plus 2 cosine x equals 0. Again, we're going to replace our sine 2x with 2 sine x cosine x plus 2 cosine x equals 0. Again, looking at the left side here, we should be able to recognize that a cosine x is factorable. So we take that cosine x out as a common factor. We'll have 2 sine x plus 1 equals 0. Actually, I'm going to remove a 2 cosine x, couldn't I? So that I'm left with, you need to be very careful there, a little more careful. If I remove 2 cosine x, I'll be left with sine x plus 1 equals 0. Okay, now by the way, this would probably work if I just removed cosine x and got 2 sine x plus 2. Still would work, of course. Doesn't matter. So I got 2 cosine x equals 0, using the zero product property, and sine x plus 1 equals 0. So that's going to give me cosine x equals 0, and it's going to give me sine x equals negative 1. So we're looking for the general solution where cosine x equals 0 and sine x equals negative 1. We got 2 equations to solve again. Let's consider both. Let's draw our unit circle again over here. Consider our points on the unit circle. X is 1, y is 0, 0, 1, negative 1, 0, and 0, negative 1. Okay, so where is cosine x equal to 0? Cosine being the first coordinate. Cosine x is equal to 0 here and here. And again, that's just between 0 and 180. We're looking for the general solution again. So it's going to be all of those locations as we continue to rotate around. So we got cosine x is equal to 0 at pi over 2, at 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on as we continue to rotate. So we write that general solution as x equals pi over 2 plus pi n, where n is number of I. Now what about sine x equals negative 1 half? Sorry, negative 1. Sine x is equal to negative 1, sine being the second coordinate, right there. Sine being the second coordinate is right here. So we would write x equals 3 pi over 2 plus, we got to continue to rotate we got to continue to rotate now 360 degrees or 2 pi before we get the next answer. So it's going to be 2 pi n, where n is number of I. If we look at the solutions here and the solutions here, you should be able to recognize that every solution that exists here also exists here. Because remember, we said pi over 2 was a solution plus pi n. So 270, or 3 pi over 2, was a solution. So this was a solution every time as we continue to rotate as well. So every solution that I get here also exists here. So this solution would represent all the solutions. Pi over 2 plus pi n, where n is number of I, or pi k, in this case, correct answer is D. In terms of any non-permissible values, there are none, because if you look at your equation contains both sine and cosine. no non-permissible values associated with sine and cosine. So we're good. But recognize here again that all of these solutions are included in this solution set here. Now all of these aren't included here, but all of these are included here. There are answers in this set that are not included in this set, but all the answers in this set are in this set. So this set will include every possible solution. Question number 4. Solve for all possible values of x in radians. Solve for all possible values of x in radians, and we got 4 sine x cosine x equals root 3. Okay, let's do it. If you look at this one, you're probably thinking, there's not a lot I can do with this. But the reality is, yeah, there is something we can do with this. I'm going to rewrite the 4 sine cosine as, let me just delete that again, as 2 times 2 sine x cosine x equals root 3. So I've rewritten that. And the purpose of rewriting it, hopefully you will see, will enable me to now rewrite my 2 sine x cosine x as 2 times sine 2x equals root 3. Of course, when I solve this for sine 2x, I get sine 2x equals root 3 over 2. So again, what we need to do here now is we need to let 2x equal theta. We're back to what we did actually in chapter 4. Back in chapter 4, we let 2x equal theta, and we solve for theta. So I got sine theta is equal to root 3 over 2. Now let's solve this for theta. Solving for theta, using again the unit circle here, where is sine equal to root 3 over 2? Considering the fact that sine is positive in 2 locations. Let me just highlight this for you. C-A-S-T, sine is positive here and here. And of course, if sine is root 3 over 2, cosine is a half. So there's the coordinates of the point right here. And the reference angle you should recognize is going to be, well, we got 1/2 of root 3 over 2. That's going to be 60 degrees or pi over 3. Pi over 3 is my reference angle in both cases here. Reference angle of pi over 3. So I'm going to write my general solution for theta as pi over 3 plus 2 pi n, where n is a number of I. That's one general solution. The other general solution is going to be 2 pi over 3 plus 2 pi n, where n is a number of I. So I've now solved for theta. I wasn't asked to solve for theta. I'm asked to solve for all possible values of x in radians. All I need to do is go back and replace my theta with my 2x. So if I replace this with 2x, let's get my final answer here. So I'll have 2x equals pi over 3 plus 2 pi n, where n is the number of I, dividing through by 2 to get x by itself. I'll have pi over 6 plus pi n, where n is the number of I. There's one general solution. And the other one, let's do it over here. Again, I got to replace my 2x now, my theta back with 2x over 2 pi over 3 plus 2 pi n, where n is the number of I. Divide both sides by 2, and I get 2 pi over 6. Now 2 pi over 6 is pi over 3. So let me just erase that, and we might as well fill it in with pi over 3, because that's what it is, of course. So it's pi over 3, dividing by 2, all the way through, I'm going to get pi n, where n is the number of I. And there's my second solution for x. Okay, that's what I wanted to do, 4 solutions. So key ideas. Key ideas: reciprocal quotient of Pythagorean and double angle identities can be used to help solve a trigonometric equation algebraically. And we need to check that solutions for the equation do not include non-permissible values from the original equation. I didn't do that with the last example. Maybe I'll go back and do that in a second. And unless the domain is restricted, you give general solutions, which is exactly what I've been doing in this lesson. For example, 2 cosine x equals 1, the general solution would be pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n, where n is the number of I. In the domain between 0 and 360, the solutions will be 60 and 300. But again, we're looking for general solutions in this case. Now, I did say I should go back and just make sure that there are no non-permissible values in the last example. If you look at the original equation involved both sine and cosine. There are no restrictions on sine or cosine. There are no expressions here that have restrictions associated with it. So my 2 solutions that I found are okay. There are no non-permissible values here. And that ends this lesson.